Alright, welcome back everybody. In this video we're going to talk about material from section 9.3 of AP Calculus, finding arc lengths of curves given by parametric equations. And it has not been very long since we found arc lengths of curves given by Cartesian equations, so this should be fairly fresh in your mind. And I'm going to harken back to what we talked about then. Basically what we did to find the arc length of Cartesian curves was we used the Pythagorean theorem to find the length of a small piece of the curve, and then we used integration to sum up all of these. And depending on what variable our curve was in terms of, that established, basically how we manipulated this square root of dx squared plus dy squared to get the appropriate differential in our integral that we needed. And so, when we had y as a function of x, we, multiplied through by dx and divided everything in the square root by dx quantity squared and simplified. When we needed our curves to be in terms of y, we multiplied by dy and divided everything in the square root by the quantity dy quantity squared. And we integrated from the starting point to the ending point. If it was, in terms of x, we went from a to b. If it was in terms of y, we went from f of a to f of b, based off of my picture that I have up here. Alright, so I hope you all remember doing that. When we have parametric curves, they're written in terms of t. So we're going to multiply by dt and do a little bit of manipulation, and we end up with this formula for the arc length of a smooth parametric curve. So if we have a smooth curve, x equals f of t, y equals g of t, notice what it says here: if it is traversed exactly once, as t increases from a to b, then the curve's length is integral from a to b of square root of dx dt quantity squared plus dy dt quantity squared with respect to t. So everything is in terms of t here, limits of integration in terms of t. This phrase right here that I highlighted, traversed exactly once, is an important one. It says this works only if the curve is traversed exactly once on the interval. So it's possible that the curve might be traversed more than once. And if so, we need to find the appropriate time values that represent exactly one traversal of the curve. Don't just blindly integrate using these endpoints of our time interval as the limits of integration. You want to make sure that that produces only one traversal of the curve that you're talking about. Second thing, sometimes curves contain pieces that are symmetric. When that's the case, we would frequently be well served by, taking and finding the length of one piece and then using the symmetry to calculate the length of the entire curve. In fact, in the last example in this lesson, we're going to look at a situation where we have a curve that is not smooth, but we're going to use some symmetry in order to calculate the length of that curve and overcome the issues that we would have with a non-smooth curve. Alright, so let's get to it. Let's do a couple of examples. Should be a fairly straightforward lesson here. Example 1, determine the length of the parametric curve given by the following parametric equations. So first I want to find dx dt and dy dt. Dx dt here is 3 cosine of t, and dy dt is negative 3 sine of t. And so our integrand here is going to be the square root of dx dt quantity squared plus dy dt quantity squared with respect to t, and we're going to integrate from one end to the other. We need to verify that we traverse the curve exactly once from 0 to 2 pi. Now in this one you can probably imagine what, sine and cosine, we go through the entire cycle of sine and cosine values going from 0 to 2 pi. So this should produce a single traversal. I'm just going to, show you to double check. A lot of times what I will do is I will just go on my calculator here, and especially if this is a calculator section, usually if you see these on your AP exam, they will either be on a calculator section or they might give you a picture of the curve to help you determine, where the traversal happens. So let's do this from 0 to 2 pi. Okay, should fit on my window. I'm going to go ahead and path this so that I can see if it writes over top of itself. And I'll go ahead and graph this. And there it goes. And it stops when it gets to the end here. So this is exactly one traversal. What might happen, say I gave you the interval from 0 to 4 pi here instead. That would be a situation where if I graphed this from 0 to 4 pi, you would see that this function traverses the curve more than once on that time interval. You see how it's tracing over top of itself. That would mean that I need to find where it stopped, where, that first trip around this path stopped, which would have been at 2 pi here. So we've got this all set up. Now we're going to go ahead and integrate. If this is on a calculator section, I'm probably going to use my calculator, but this problem is one that we can do by hand. Might not look like an easy one from here, but it actually works out pretty well. We're going to have square this out and square this out, and when we do that, we can take the square root of 9 out of that radical, and this becomes the integral from 0 to 2 pi of square root of 9, which is 3, times the square root of cosine square root of t plus sine square root of t, which everyone should recognize as 1. And so this becomes the integral from 0 to 2 pi of 3 dt. The antiderivative of 3 dt is 3t. And when I evaluate that from 0 to 2 pi, I get 6 pi as our length of that parametric curve. All right, let's look at the next example. Determine the length of the parametric curve given by the following parametric equations. So first I'm going to take my derivative, dx dt and dy dt, and set up my integrand. And so this integrand becomes square root of 9 cosine of 3t squared plus negative 9 sine of 3t, quantity squared, with respect to t. And now I just need my limits of integration. So let's see, the only thing that changed here is we put a 3 inside the parenthesis. All right, and we're still from 0 to 2 pi. Oh, I got to change this back to 2 pi from my hypothetical situation. And now we'll look at the graph. And here we see that the graph does trace over itself multiple times. And so we need to figure out where this stops. So I'm going to go ahead and trace this, and it should be pretty easy for me to find. Looks like right about there. Ooh, this is going to be helpful if I change my window. Instead of being 0.1, if I change it to being in terms of pi. Usually I do like pi over 30 or pi over 36 or something along those lines. Let's do pi over 36. Pi over 36 is really nice because it hits all of the major pi values. Gives us a nice curve, doesn't take too long to do it. So I'm going to go ahead and trace the curve now. And to get around one time takes me to 2.094. I don't know if you recognize that, but that's 2 pi over 3. You should have been able to figure that out from the fact that what's inside the parentheses here is 3t, and so we're looking for how long it takes for 3t to cycle through 0 to 2 pi. So you're looking for when 3t is equal to 2 pi, and that tells you the time interval where we're going to get to the end of that interval. So we're going to integrate this from 0 to 2 pi over 3. And so we're going to go ahead from there. And again, I can do this by hand. This becomes 0 to 2 pi over 3, square root of, and that's going to be 81 cosine squared of 3t plus 81 sine squared of 3t. So that's just going to be the square root of 81 when we simplify it. And this becomes the integral from 0 to 2 pi over 3 of 9 dt. And therefore, this is going to be 9t evaluated from 0 to 2 pi over 3, which is equal to 9 times 2 pi over 3, or 6 pi. Astonishingly, the same length as the last curve, and really, it looked exactly like the last curve, the only problem being that it traced over that curve 3 times, and so we ended up we ended up having a different integrand here and different limits of integration, but it still was the same. The curve was the same length. We just traced over it multiple times. Okay, we're going to stop here for this video. We'll come back and do one more short video with the last example from this lesson, and we'll talk about this then. All right, everybody, have a great rest of your day, and we'll see you next time. Bye-bye now.